a beautiful scene. This is actually related to my topic tonight. This is called scene perception. We'll be teaching computers how to recognize such places, such scenes, by using computer vision and machine learning. This is actually the palace of Versailles in France. So, this is the first paper, What Makes Paris Look Like Paris. So it's a team from Carnegie Mellon University and École Normale Supérieure in Paris. So their motivation actually is, ultimate goal is to provide a stylistic narrative for a visual experience of a place. So such narrative can be related to others, highlighting similarities and differences across regions. And they claim that this is one of the few papers that is the front runner for this emerging field, which they call computational geocultural modeling, where they try to do just that, modeling geocultural influences through a wide geographic area. More precisely, their goal is to aim to find a few hundred visual elements that are both repeating and discriminative. So this is actually a picture from Paris, and this is a picture from London. So when asked in an informal survey, most of the participants get this correctly, that this is from Paris. So besides the text over here, I think it's blurred in their survey. Besides the text, the participants say that some features actually give it away. Like for example, the balcony is over here, the window style, and this street sign over here. While in this one, it's distinctly from London by the pillars or the style of the balconies. And so they wanted to get this automatically. So they collected their data. They find that Flickr and other photo sharing websites are biased towards famous landmarks, and they didn't want that. So what they wanted to use was actually do a street view, which takes everything besides the famous landmarks. And what they did was they scraped panoramas from an area. As you know, the Google Street View has a special vehicle and drives along the streets. So they get the panoramas from an area. They get two images, both parallel to the vehicle. And for example, in this case, one here and one here. And they get 10,000 images per city. And their cities are cities in Europe, cities in America, and city in Asia. And of course, the Paris is the focus of their paper here. So they actually tried a lot of other algorithms, like trying SIF or trying histogram of gradients, but they find that the initial k-means cluster was unsatisfactory. So they developed their own algorithm. So first off, their algorithm begins with this step, candidate clusters generation. So they just sampled 25,000 high contrast patches for candidate seeds, right? And they were represented each by their histogram of gradients and color descriptors. So histogram of gradients is one such feature descriptor, just like SIF or LDP. So they defined G-informativeness by getting the top 20 nearest neighbors. And well, they divided their set to actually the positive set and the negative set. The positive set meaning the set that is in Paris, the patches that is in Paris, and the negative set, everything else. So they kept the patches that are mostly in the positive set, right? So then they removed the duplicates from that set, and what they came up with is 1,000 candidates, initial candidates that they hope to become refined so that they can get better images or patches. So for example, this is one of the patches, and they get its nearest neighbors. And as you can see, the red bounding boxes are actually not from Paris, they're from the negative set. But they still survived somehow, and they wanted to refine this set even more. So for example, this set, it turns out all the nearest neighbors have black bars in the side. This is because for normalized correlation, all pixels and regions are treated equally. So they think that these pixels are also important. So what they wanted to do is to refine this more. So they tried to use a classification scheme everyone is familiar with, I think, SVM. So they divided the data to 3, taking the initial candidates, that's actually 4 parts to the data, right? So 1, 2, 3. This is the initial 1,000 candidate clusters. They will train the SVM to recognize the 1,000 here, and they will apply it on the new unseen data, right? And then they will get the top k nearest neighbors in the positive set as the positive. They will iterate the learning. So what's next is they will then train on this and then apply on this, right? So they use the top K detection from the previous round as positives. So as you notice, they're trying to improve the SVM, and they're trying to make it generalized because they haven't seen these data before, right? So they repeat that 3 times. Now they have this exit criteria. When the SVM accuracy is low on an iteration, the SVM that recognizes a patch becomes deleted, so it doesn't survive. And then at the final one, they rank SVMs based on the accuracy, which is the percentage of times it fired on the Paris positive dataset. So at the end of this all, they will have around 1,000 SVMs that can recognize patches from Paris. So for example, this is what happened. This is the initial clusters from the previous round, and they will train the SVM, and turns out this is its detections in the first set, and they're still wrong here. This is from the positive set, negative set, and in the future iterations it improves. As you can see, it now recognizes the Parisian balconies, right? So Parisian balconies turns out like this. The idea itself is not new. They just use this idea from another team from previous years. And so they validated their SVMs by, first off, they ran the top 1,000 Paris element SVMs or detectors on an unseen dataset. So 50% of that dataset is from Paris and 50% is wherever else. They computed the number of times the SVM fired in Paris, and turns out it's 83% accurate on Paris, and in Prague it's 92% accurate, meaning maybe Prague is easier to recognize than Paris. They also tried human evaluation, so they just gave 100 visual elements to people, 15 Paris and 15 Prague. Out of this 50% was given by their initial or their SVM detectors. And then they just wanted to know that from their algorithm selected patches, the classification accuracy, which turns out to be quite high, 78.8%. Again, another
what was the previous, the algorithm, what was the classification accuracy?
Oh, the previous one, it was 80.
So it's better than the human.
Yes.
Value.
Or maybe the humans here are getting tired. 100 images. So they also tried to hire an artist to draw Paris for 10 minutes. So this is his sketch. And then after several days, they gave the sets, the features that they discovered to that artist and asked him to draw Paris again. And here's what happened. It's a bit small here. This is the sign, and these are the balconies. And then they made a survey. 10 out of 11 said that the second one was more in Paris. Alright. So they did it on other cities as well. So Paris, you'll see here the balconies, the windows, the signposts, street lamps, and the signs. It's interesting to note that in Barcelona they have trees as well. Suggesting they don't have trees there. Just kidding. So they also try to explore different geospatial scales, not just in Paris. So they try to get their SVM detectors and run it on different cities, and they found correspondences. So for example, that's the arcs or the doors or the balconies in different places. And then using that, they can actually make a visual correspondence map. So for example, they just take the positive set to be all the cities that I want to be part of my set. And I wanted to see what is the similarities, similar patches. That this is plainly wrong. But yeah, we can really see the different kinds of values. Yeah, it looks like a lamppost. Ayan, so that's the first paper. That's actually very interesting. I found it very interesting. The second, I theorized that maybe it looks good. Maybe the algorithm would output GPs. I think, it's unique. Or traffic. So yeah, that's the first paper. The second paper is 80 million tiny images, a large data set for non-parametric object and scene recognition. So out of the bat, this is more than just scene recognition. It's a team from MIT, and this montage is actually their data set. It's represented that way. And their motivation for this one is, with overwhelming amounts of data, many problems can be solved without the need for sophisticated algorithms. Their example is from Google search, did you mean query? right? They did not parse the data or did not parse their query in complex ways. They just memorized the query answer pairs, and the results were acceptable. So their main question was, how big does the image data set need to be to robustly perform recognition using simple nearest neighbor schemes? So they're just using here k nearest neighbors. What they did, obviously the data is very large. First off, they got WordNet to provide a list of non-abstract nouns, 75,000 abstract nouns, and they ran that query term for 7 independent search engines, and the program ran for 8 months. Right? So it gathered 97 million images. And then out of those 97 million images, they removed the intra-word duplicates, which I assume is some kind of synonyms. And they removed the images with low variance. They normalized the brightness and the contrast, and they downsampled down to 32 by 32 images. Now, the images are labeled with the search word and the URL, and it's accessible here. The reason why... Pero they argue that it can fit in a hard drive. So maybe 8 months too. 8 months download.
Yun sa kanila yan, MIT high bandwidth network dito.
Twice.
Twice?
Nawala pa ng internet.
So they obviously had to store this data somewhere, right? So 32 by 32, that's one of the reasons why we need the sample. Pero kasi they have other reasons as well. So they ran, they made humans evaluate the scenes on low resolution images. And they found that this here is the image resolution and this here is the classification rate on that scene recognition task. They found that from 64 to 32, the decline was not too large, but from 32 to 60, it was very steep. So they determined that 32 perhaps maybe...
So is this a general thing that this is applicable to all images?
Only for their... actually, that's just a small data set. For our samples.
So this is an interesting result, right? So compared to patch, if it is color or grayscale, if your size is 64 by 64, valuable na yung color. Wala naman masyadong importance, diba?
Yeah, but for 16 to 30,
yes, of course. If you have smaller patches, then the color would give you more information.
I haven't really what kind of data this is. You just mentioned this. Also on car detection, the humans still outperform the best computers, the best algorithms. These here are models, computer models, or computer classifiers. And each of this is the ROC curve. And humans actually are better even at low resolution images in detecting cars. Right? So this useful resolution, humans use just low resolution. They still get it right. So another statistic they define is defining the similarity measure. This is just actually your standard square difference. But for faster retrieval, they index images over the first 19 principal components. And then afterwards, when they get matches, they just compute the entire, the exact square distance.
Faster access.
Yes. Of course, they said that that initial measurement was not invariant to small translation. So they developed new image similarity metrics. So this is V-warp, and this is V-shift. And the results were actually more convincing. They argue that in their experiments, pixel shift or V-shift actually worked best. So you'll see the experiments in a while, and they're also interesting in their own right. But first off, let's just discuss this. They used WordNet again for the voting scheme. So we know that WordNet has a semantic hierarchy of meaning, and they have a lot of labels in their data set, right? So there are lots of labels, and maybe an animal can be 2 species at a time, but they're also animals. So what they can do is that they can handle that in different semantic levels. So the idea is something like this. So we have a vice here, which is a kind of instrument. We get its neighbors, then we get its each neighbor's vote. They construct this tree, and perhaps just at each level, they will try to find the maximum votes. So for example, at this level, it's a device. At this level, it's an instrument. At this level, it's an artifact. Of course, there are other votes, but they're trumped by this branch over here. By this algorithm, they had a lot of interesting applications. One such thing is scene recognition. So they wanted to distinguish scenes and objects first, and they achieved that well. This is the ROC curve and the precision recall curve. They can also go for a finer detection. If they want to see just cities, if you want to detect cities, well, they just find the neighbors that are, is it indeed a city. So you'll see here that actually mountains is the best ROC curve, suggesting that mountains are the easiest to distinguish. And they have a lot of other applications, like as well as scenes, we can also go for persons, which is just change the mode to detect persons. And then for portion localization, you can just make crops and then get again its neighbors, and you can find optimal crop. And this is general image annotation. So as summary, there's a lot of experiments. So this is their main contribution or conclusion. The vast majority of effort in the recent years has gone into the modeling part. In contrast, this paper moves in the opposite direction, exploring how the data itself can solve the problem. And this is the different points. They have evidence that 32 by 32 is the best or the minimum image resolution for recognition. They compiled this really, really large data set, and they explained with lots of applications how people can use this data set. It's important to note that Google scale 2 billion yung images. Sa kanila 7.9 million na. So the performance can actually be better using Google scale. Okay. So, this